115.
150.
15.
115.
15.
Okay, okay. So one answer we have is 127. Other answer we have is 115 centimeter. Any other answer? Let me zoom it for you.
Sir, 1 to 2.5.
1 to 2.5. We have three answers for mean length. Any other?
Sir, 130.
130. Who is it? Kanishk, right?
Yes.
Yeah. So apparently 130 centimeter is the correct. And let me tell you how you could have computed it with precisely. See, this length is 30 centimeter. Okay, and when we are computing L2, we are measuring from this point to this point, right? So this 30 and this is half of 10. So this should be 5 centimeter. This is 30 centimeter, and this is 15 centimeter. But we should not go entire 15 centimeter. When we are measuring the mean length, we should get a stop here with 7.5 centimeter. And now this is from this point to this point, it is also 7.5 centimeter. Okay, so let me remove it. Okay.
Sir, it is rule that we have to go mid of the core section to measure the mid length.
It is not a rule. That's why we talk in terms of mean length. In problem solving of such type of questions, if you are considering mean length, it means you are taking care of the entire code. Okay. So, what approach did you apply for the computing? If you are not considering about midpoint of the code, then what could you consider? You let me know your approach. Okay. Go ahead if you have something in your mind.
Sir, but we can also go from inside, not 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 correct midpoint.
Okay, you mean to say that shortest distance you want to travel? Let me highlight that.
Yes, sir.
Okay. If you are considering the shortest path, then the thing is your flux is flowing through the entire core. Okay, your flux is flowing here also. Your flux is flowing here also. So if you are considering the shortest path, then the reluctance for the longest path, since you are not considering, it means you are underestimating your reluctance, right? If there are some flux flowing in this area, let me tell you, and you are considering only the shortest path, then you are underestimating the flux. Or if you are considering only the longest path, then you are underestimating the reluctance. And if you are underestimating or overestimating the reluctance, it means you will not be able to supply appropriate current to the winding, which will be responsible to channelize the flux through the core. Right. So that's why for analytical calculation, many people take midpoint. So they go from midpoint to midpoint such that it should be accounted for the inside point of the core as well as the outside point of the core. Did you get it?
Yes, sir. And sir, why we did not include L1 during the calculation of mean length?
No, no, we have to consider L1, right? We haven't considered yet. We are computing only L2 just for now. We will come to L1. Since the
Okay,
width
sir.
of L1 is different, so we have to handle that a bit differently. Just for the time being, we are avoiding. Okay.
Yes, sir.
Yeah. Okay. So this is again 7.5. This is 7.5. Okay. And this is 30 itself is given. And this is again half of 10, which will be 5 centimeter. Now we have just to add all the lengths, which is 35 plus 15, 40. Okay, 40, 30, 70. 70. Let me take the help of calculator.
Yes, sir. 130.
Okay, so it is coming as 130 centimeter. Anyone is getting mistaken, or anyone who is not able to get 130 centimeter, getting something else? Okay, so I hope everyone is getting 130 centimeter of L2, right? So let me write it. L2 as 130 centimeter. Our approach is to break this core into two part of reluctances such that, and at the end we will connect it in series or parallel by whichever convention you see and whichever way you see, and then we will connect both reluctances in series and parallel, and we treat flux as a current. So I hope many of you know the magnetic equivalent circuit as MMF is generally made analogy with EMF, and resistance has been made analogy with reluctance, and we consider current as similar to the flux. Okay, so these are the analogy we bring from our very vast experience from the electrical circuits. So we utilize our knowledge of electrical circuits and we apply here in the magnetic circuits, and we see that MMF is the source of flux, whereas in electrical circuit current is the uh, voltage is the source of current. Okay, we have some voltage source that is able to produce certain current in a wire or in a closed circuit, and in an electrical circuit we have something known as wire resistance, whereas in magnetic circuit we have core, which we call as a reluctance. So basically reluctance, the higher the reluctance of the core, the lower the flux of the uh, that machine or whatever the core is. Okay, so the lower reluctance will allow you to flow the higher amount of flux through the core, but it is not as linear as electrical circuit. This core, this silicon steel, these ferromagnetic materials have many non-idealities, many non-linearities. Okay, so there is some limitations till what point you can increase the amount of flux when you increase the current. So this is the H MMF and this is the flux. Okay, so if you keep increasing your MMF or electric field or whatever the current source, it your flux will increase till certain point, And after a certain point, non-linearity of the core will get introduced in the core, and it will start getting in saturation region. So after certain field, after certain magnetic field, you cannot increase flux in the circuit, because the property of ferromagnetic material, it it does not allow flux density after a certain limit. It will be, it will increase, but it will be very less. It will be incremental change. Okay, I hope it is clear. So we were at L2. We have computed the value of L2. Now, since we have to compute reluctance of the L2 section, so I am calling it as R2. R2 is nothing but L2 by mu into A2. So second thing is we have to compute A2, area of this cross section, area of the cross section where L2 is covered. So how much that area will be? Could anyone let me know? Cross-sectional area is nothing but the depth of the core. Okay, whatever the length along the z direction, if you are seeing this in x and y direction, whatever the length in the z direction, okay, multiply with the width of the core. Okay, so for L2 section, we have uniform width, that is 15 centimeter. Okay, so
Yes, sir.
yeah, so we have width is equal to 15 centimeter, and we have depth of 10 centimeter, which is written here from the problem if you couldn't figure it out. So depth along the z direction is 10 centimeter. So we can compute area 15 centimeter into 10 centimeter, which will be 150 centimeters square. Okay, if we convert into meter square, it will be 0.015 meter square. So this is A2. Now we know the value of L2 and A2. So we can compute the reluctance very easily. L2 we have computed as 130 centimeter, which means 1.3 meter, divided by mu. Mu will be mu r into mu naught. So mu r is provided as 2500. So, and sorry. So this is the mu. This is the value of mu. Mu r into mu naught into A2. A2 we have computed 0.015 meters square. So please compute it for me and let me know the value of R2. Anyone? So keep that right. Hi, sorry for disconnection. Anybody computed that value of R2? Okay, so let me write the value. I have computed it. I have the value 27,600. What will be the unit of reluctance? I think Bhumika has already computed that value. Yeah, so you are very close. You have commented that 27,586 per meter. Per meter, I would not say it is correct unit. Okay, so per meter is not a correct unit for that. You think in terms of, you know, MMF by flux. So MMF is nothing but NI, and its unit we write as ampere turns. Yeah, Prasad, you have just answered partially. Ampere turns is correct. Ampere turns is the unit of MMF only, but flux has some unit, right? So ampere turns per Weber. That should be the unit of reluctance. The unit of flux is Weber, so it is ampere turns per Weber. Yeah, that's correct, Koteswar. So it is ampere turns per Weber. We have computed R2 reluctance of uh, this uniform portion, uniform width of 15 centimeter portion. Okay. And we have another portion which is indicated with L1. Okay. So please let me know what is the L1, what is the value of L1. From the figure, how much you can see that L1 is.
45 centimeter.
45 centimeter. That's correct. Yeah. L1 is 45 centimeter. How much the area of that section is?
One 150.
150 centimeter square.
Yes, sir.
150 centimeter square. It doesn't seem correct. Why? Any other answer of A1? How did you compute 150 centimeter square?
2 to 5.
225. It is also not correct. 225. 100 centimeter square has been answered by Abraham. Yeah, that is correct. 100 centimeter square is correct. Why, where you guys are doing mistake here? I am not able to get it. See, the depth is fixed along the z direction, that is 10 centimeter. Only thing we have to know is the width of this section. Okay. So width of this section is 10 centimeter only. So I don't know. The guy who has computed 225 centimeter, he must have considered 15 into 15, and I am not able to see anywhere 15 into 15. And other guy must have done 15 into 10. That is also not correct. So 100 centimeter square, it's 10 into 10. Okay. So now we have L1 and A1. L1 is 45 centimeter. A1 is 100 centimeter square. We can compute now reluctance of this section L1 by mu A1, that is 0.45 into 45 into 10 raised to the power minus 7 into 2500, I guess. Relative permeability is 2500. Okay, A1 is 100 centimeter square, it means 0.01 meter square. So how much it will come out? So it will come out to be 14,300 ampere turns per Weber. Okay, am I correct? Okay, so now we are done with reluctance calculation of both the section. Okay, you can see that the reluctance of both the sections are different. So that's why we computed both of them separately, and now we want to compute the flux. So since we know the magnetic equivalent circuit, we have the MMF, we have the reluctance. So since we have computed two different reluctances, so should they be connected in series or parallel? Or if it is in parallel, why? Or if it is in series, why then? Anybody? No idea? At least make a guess. Whether both reluctances should be connected in series or parallel.
parallel, so
Parallel.
Parallel, someone is saying parallel. Okay, I don't know why they are saying parallel, but okay, let us see. What happened in an electrical circuit? If we have something like this electrical circuit, okay, we have some current flowing, we have a resistance here. Let us consider this one resistance and this one resistance, and we have this mmf source. Okay, now can are you able to visualize it?
series connections.
Series connection, yeah, exactly. Why? Because in series connection of circuit also, current flows is same for both the portion, right? Here also the flux will travel through the core is same whether it is R1 section or R2 section. Okay, so they should be connected in series. So let me go ahead and connect them in series. And at the place of V, we have Ni, and it is stated in the problem that if we are providing 1 ampere of input current, okay, and the number of turns is 200 turns is given, then how much mmf it will produce? So it will simply produce 200 into 1, 200 ampere turns is the mmf. Now some flux will flow. We have already computed the reluctances. How much it is? 14,300, and the other one is 27,600. Okay. So now we have simple and electrical circuit. Okay. We just have to apply magnetic Ohm's law. That is phi is equal to 200 divided by 27.6K plus 14.3K. How much it will come? So from my calculation, it is coming out to be 4.8 milliweber. Okay, I hope it is correct. Any doubt in this problem? The first step was to compute exact mean length turns. Okay, and I also observed many of you did silly mistakes, which is not allowed in the GATE exam what you are going to write. So please do not make any silly mistake. Yes, Bhumika, it is not 4.7, it is 4.8 milliweber. Okay, and also for the calculation of area of the cross section, very carefully judge. We have to deal with cross sectional area. Okay, so now I guess I can move ahead to another problem if no doubt in this problem.
Sir, what if in the case the reluctance is in parallel? So
Okay, so reluctance is in parallel when when current becomes in parallel. What happened to the current when your resistance connected in parallel? You visualize an electrical circuit. What happens to current? Let me draw it for you. When you have some
Current
parallel,
will be divided into
yes,
branch.
exactly. Current will not be equal throughout the wire, right? Some current will be here, some will divided through this resistance, other will be divided through the second resistance. Okay, this is R1, this is R2. But here, if you see throughout the core, this flux phi, it is uniform. Okay, it does not have any other path to flow, right? So it cannot flow to some other air or whatever. Why? Because it is the least reluctance or least resistive path. So this is the core is the permeable path, so it will follow the core. Did you get the answer?
Yes, sir. But if there is any chance that it having a parallel connection, and what is the formula that it should be used there, sir?
Yeah, definitely. Definitely. There are scenarios where you can have parallel connections. Let me show you. So if you have such kind of core, let me draw it. Suppose you have supplied a voltage source and it is some current is flowing in the winding. Now because of this current, some flux will flow. Okay, flux will come till this point, and what will happen? See, whatever this section, all of them are core. Okay, and do not get confused, please. These all are cores, and whatever is not covered, the unshaded portion is air. The shaded portion is the core. Now you tell me, uh, the flux will start to flow, and it will come here. Okay. Now it has two paths. One path is to go this way. Other path is to go this way. Okay. So it has to cross this air gap, which is generally very small, and it will complete its path to both the way. So whatever flux was here, consider it as phi. Some portion of phi as phi1 will traverse through the air gap, and some portion of phi as phi2 will travel through the other portion. So here you can see we have phi is equal to phi1 plus phi2. Now, after this session ends, you just compute the reluctance, how the reluctance will look like, how the connection of the reluctances will look like. Let me just draw that for you. So if you have this Ni, okay, in middle section, you will have two reluctances. Why two reluctances?
Two mediums, air and core.
Yeah, that's correct. R2. Now, am I missing something? Am I missing something? The reluctance of the left side, where this phi will be traversing. Okay, so this is your parallel connection, right? Now I hope you got your answer right.
Yes, sir.
Okay. Any doubt in this? I hope not. Anyone has any doubt in this parallel connection? We will solve some more problems so that you will get idea. Okay. Now read this question carefully. Here, one core is there and one rotor is there. Okay, in the air gap of this core. Now here also we have to compute resultant flux density in the air gap. Okay. So first thing is that we have to draw an equivalent circuit with whatever supply, which is 200 ampere turns. Okay, that is the only supply in the circuit. Okay. Now, since we have to compute flux density in the air gaps, we must compute the flux in the circuit, right? Then we are given with area, we can compute flux density. The next task of ours is to draw and draw reluctance or identify how many reluctance in this circuit is. So for this network to be completed, how many reluctance elements will be required? If you are not able to visualize, this portion is the stator. Okay, this all black shaded portion is the stator. Okay, this is one air gap. This is a rotor. This is another air gap. Okay, and again the stator. Okay, so a stator, rotor, and air gaps. How many reluctance element I need to draw in this circuit?
So two reluctances.
Two reluctances. Any other answer?
So four,
Four reluctance. So is this four?
uh, including two cores and the two air gaps.
Yes, yes, that's perfectly correct. We have to model it with four reluctances. That is correct. Yeah, so why four? Let me explain it to you. As Vignesh has also explained, that one reluctance will be corresponding to this core. Okay, other reluctances will be corresponding to the first air gap, okay, which is facing, and other reluctance corresponding to the rotor. So this will be third, and the fourth reluctance will be corresponding to this again air gap, and which will be completed via this path. I hope everyone has got it.
Yes, sir.
So
Yes. Yes.
great, great. So let me model it with four. The stator, uh, air gap, rotor, air gap. Okay, these are the four reluctances. Now the task is to compute all the reluctances. Then we will be ready to compute flux. Okay, so for computing uh, reluctance of the stator, we should have the length of the mean length of the stator core divided by permeability into area of the stator core. Okay, so how much is the length of the stator core? Let me remove it so that you can visualize.
50 centimeters.
50 centimeter, that's correct. So 50 centimeter is the length which is also provided in the problem if you read carefully. And area of this stator is also provided as 12 centimeters square.
12 centimeters.
So it is 50 centimeter divided by, and the relative permeability of the core is 2000. So 2000 into 4 pi into 10 raised to power minus 7 into 0.0012 square. Okay, so whatever this value will come, that will be the value of a stator reluctance. Next is the rotor reluctance. Okay, so rotor length is given as 5 centimeter, and I think area also should be given. It is 12 centimeters square. Okay, so 12 centimeters square of the rotor area. So again, let us compute 5 centimeter, which will be 0.05 divided by 2000 into 4 pi into 10 raised to power minus 7 into area is same. Okay, now the reluctance of air gap. Okay, air gap 1. Though both the air gap length are same, so whatever the reluctance of first air gap, that should be similar to the second air gap, and the length of air gap is provided as 0.05 centimeter. Okay, and the area of air gap we have to identify. Okay, and I don't think we need to identify since it is also provided in the question. It is 14 centimeters square. So the length is 0.0005 meter divided by 4 pi into 10 raised to power minus 7, because we do not have to take relative permeability since it is an air medium. The area is 14 centimeters square. Now, I guess you must have computed the reluctances. So how much overall reluctance is coming, that you have to let me know. R equivalent is RS plus RR plus 2RZ. So that should come out to be, you just match on your own. That should come out to be 751,000 ampere turns per Weber. Okay, I hope you are also getting the same value. And the MMF we already know that is 200 ampere turns. So I guess we are ready to compute the flux. Flux is 200 divided by 751. That should come out to be 0.00266 Weber. Okay, any doubt till now? But the question was, what will be the resulting flux density in the air gaps will be? So how to compute resulting flux density in the air gaps? It is nothing but the
Flux by
huh,
area.
flux by area. That's right. So flux we have is 2.66 milliweber, and area of the air gap is 14 centimeters square, right? So 0.0014 meters square. So it should come out to be 0.19 Tesla, right? I hope it is fine. Any doubt in this problem? Okay, so I hope it is fine for you guys. Uh, our time has come up. So now it's time to wind up the session. Thank you very much for joining. We will meet next week on the next time, right?
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you. Thank you.
Sir, this recorded video can where I can find it.
I have provided the link of YouTube channel. Let me again share that with you. I have shared the YouTube channel link in the chat section. You can access that channel. This recorded session will be updated there.
Thank you so much, sir. Very good initiative, sir.
Thank you. Thank you very much.
Thank you, sir. Sir, YouTube channel name, sir?